So after a giant chapter of Boltzmann, we have a rather smaller chapter. Yeah, I have switched places. Is it 05? 5. So I have switched places of, it was going to be Metropolis. We were going to solve Ising model, but instead we are going to do Langevin dynamics. Okay. Well, we start with Brownian motion. Or Brownian motion. This chapter could easily be also called Einstein, okay, because it mainly concerns the ideas developed around Einstein's 1905 paper on Brownian motion. So the idea is that, I think it was in the middle of 19th century, the botanist called Brown realized that if you put something small under a microscope, it would jiggle. He thought that, for example, he would get pollen from flowers, and it would jiggle, right? He would put it in water, but put oil on top of it, it would still jiggle. He would put non-living things, it would jiggle. So he realized that it's not jiggling because it's living. Even the non-living things are jiggling. But he couldn't understand it. Then in 1905, Einstein realized that could be that it's just a pollen receiving random kicks from gas atoms or fluid atoms, whatever, like depending on where you put it. Let's say on top of a water, it would receive random kicks from atoms. And although we had pretty good ideas, nice theories that were pointing to atoms, it was sort of out of fashion in those days. And Einstein brought the idea of atom back to fashion with this study. So he showed that by studying this Brownian motion, you can actually get a good estimate of sizes of atoms or sizes of sugar molecules that were hitting. Whatever is hitting, you can have a nice idea. And he used ideas from our previous chapter, Boltzmann stuff. Okay? So, another reason I switched it to here is because it's quite related to what we had before. Do you remember this code? Like, check for collisions between balls and stuff. You are right now doing the homework on it. Well, it's the same code, but we put a pollen in it. So now we have, okay, let's say a radius of a pollen, let's say 100. Let me take this to 1. Number of balls, let's put 100. So there are masses of balls, mass of pollen, and it's the same code, right? I will describe the code more, but let's watch it first. So, okay, let me increase the radii of the balls. Maybe 10. Maybe this could be 50. I don't like this one either. let me go back to 100. And I can increase this to 3. So do you see these are the balls? They are hitting to the pollen, and the pollen is doing this random motion. This is what you would see under the microscope. You wouldn't see these guys, but you would see this one jiggling. Okay? It becomes random if you have enough particles, enough of these guys. Okay? Like, let me make it quicker. Does it seem random now? It has nothing to do. The computer is still working. That one went away. How about now? Seems random? Of course, it's not just... so there is something to it. I mean, you can write a formula for it, and inside the formula, not everything is about randomness. There is some inertia terms, drag terms, etc. So it has some directionality for a while, which is due to inertia, right? Once it starts going one way, it wants to keep going that way, but then it receives lots of random kicks. Okay? So far, so good. Do you have any questions? Let me slow it down. Reverse time. Okay. You can play with this code if you want. The trace have arrived at the same place. I don't know if I'm going forward or backwards now. It doesn't. So far, so good. So you understand the system, right? Okay, let me describe the important parts of this code. The most important new part is check for collision with pollen. So it's the same kind of collision checking, only this time masses are involved. You can see it, right? Mm-hmm. Now you see it. Now masses are involved, okay? The formula changes a little bit. Do you care? Not really, right? Okay. I mean, you can derive this formula on your own if you want, but this is what happens. If you do care, I can explain further. You do care? Yes? You just write conservation of energy and conservation of momentum again in the center of mass framework. So then things become symmetric, etc., and you get these nice formula. I can just make one comment that would be easy to understand. If M pollen is equal to M ball, then these formulas should turn into those formulas, so you can check if that is happening or not. But otherwise, we have other checkpoints. For example, energy should be conserved, right? If I'm putting new thing. And we will look at energy conservation and also something called equipartition theorem. Let me describe it to you. I actually described it a little bit, if you remember it. I don't know. So equipartition theorem tells you that, let's say you have a bunch of particles with mass m. They would thermalize and have some velocity distribution, etc., right? Let's say you put in some other things, let's say something of mass m. That's what we are doing here, right? Let me put it inside, somewhere here. So equipartition theorem is telling you that. So let me call this V. So there will be some average kinetic energy for these smaller particles, right? E kinetic energy of these small particles. They would be M. Do you understand these curly brackets?
Yes, average.
Average. Average, you can think of it as time average or ensemble average, meaning that if you have many copies of the same kind of system, okay, let's say instead of averaging it over time, you have many copies of the same kind of system. If you average the same particle over those systems, you get the same average, okay? So you get some energy here. Equipartition is telling you that kinetic energy of the big ball is going to be equal to the kinetic energy of the small ball. And in fact, anything that can carry kinetic energy will have, on the average, the same energy. Hence the name equipartition, meaning that energy is distributed equally to each system. Okay? Of course, we have mentioned quantum mechanics, and we have said that it breaks down, and that explains ultraviolet catastrophe. Do you remember that? Yes? But besides that, classically, everyone gets the same energy, which means that smaller particles would go faster and larger particles would go slower on the average. But on the average, their average kinetic energy would converge to the same value. Okay? So, do you have any objection or anything you want to add, subtract here? And also, yes, okay. Also, we know that this is kBt over 2. But we know this for a different deep reason that is buried down in rigorous thermodynamics, statistical mechanics, whatever. Just take it for granted, okay? So, big M V big M squared over 2 will also be kBt over 2 on the average, and small m, yeah. Let's see if this is the case for our code. So we go to our code. It's the same code. So I'm going to run it 10,000 times, okay? And what do I have here? I have total energy. So I'm going to monitor total energy. I'm going to print it every 1,000 steps and see whether it's the same. Do you have any question there? No? I'm going to also monitor the energy of all the small balls. So it's the average of all mv squares. M balls times v squares. Sorry, this is appearing. I'm going to also monitor one of them, just one of them, ball number 0. That's here, okay? Finally, I'm going to monitor the kinetic energy of the pollen. What do we expect? We expect that the average of all the balls, average of a single ball, average of the large ball, all of them should converge to the same value. Okay, that's what we expect. Of course, the fluctuation in the average of the all balls will be much less. It will be almost the same, because it will almost correspond to conservation of energy, because it's the energy of the system except the pollen. Yes? Because it's all balls. Okay, let's run it. Okay, we got this much energy at the beginning. Okay, 1,000 time step. Will it take too much? No, just 1.5 minutes. We can wait for 1.5 minutes, right? No? Do you have any questions? in the meantime? Yeah.
This energy of all balls thing, does it include the pollen as well? So it's the total energy of the system?
No. It's so you are asking the total energy. Total energy includes all of them. Okay, I'm printing that one. But this one, E-ball all. I mean, all the balls except the pollen. Okay? That one doesn't include pollen.
And what's being printed here?
What is printed is E total, including the pollen.
All right.
So it should be the same, and it is the same. Do you see it?
Yeah.
Any other questions? Comments? Ideas? No? Random number generation is a serious business, right?
Actually, we should do a check on it before going to the class.
I don't care about. Do you see all the balls except the pollen seems to be have? I mean, you don't see the fluctuation because I'm also drawing the others, but the pollen also converts. Actually, this is a rather nice result that it converts right on top of it. Ball number 0 wanders around, but it will come back. I mean, eventually. And I was also recording the kick force just to show you that it forms a Gaussian. Okay, those kicks are forming a Gaussian. So, you are happy with equipartition? You are happy with energy conservation? Everything is fine? Good. Now, let's move on to Langevin dynamics. Okay? Now we will have a long derivation part. That's the spirit. Langevin dynamics. Okay. I'm waiting for it to come back. Okay. Now, I think Langevin did it right after 1905, like 1908 or something. So here is the deal. Here's the Langevin equation. mv dot m times a is equal to force, right? What are we doing? What are we doing? We are taking this thing, this system, and we are trying to come up with a formula for the behavior of this giant ball, while actually modeling what's happening with these kicks. We are just going to model what's happening with these kicks. So we are going to bring this 1 plus 10 to the 23 variable thing down to one variable thing. Okay? We will represent all the kicks with a Gaussian. Okay? So, what is the effect of these kicks? Let me ask you. First of all, they create fluctuation. Fluctuation is this random force. So you have, every time step delta t, you receive a kick in random direction, and it has, sometimes it's large kicks, sometimes it's small kicks, etc., right? So we are going to represent those kicks with a with a random variable that will be random Gaussian. We will pick it out of a Gaussian. Okay. Do you have any question about fluctuation? It's just random jiggling. not giggling. And what else do we have? We have drag, okay, or dissipation. What is drag? Drag is this. So the same. So what causes this fluctuation? Random kicks. The presence of these small balls. How about if I start moving this ball in a certain direction? It would receive, let's say it's moving with a velocity v, it will receive more kicks on the front side than from the back side. Do you agree with this? Yeah. So if you sum them up, I'm dragging something and it just hits. You are running into the people with a car. So you hit people rather than people hitting you, right? So this time over here, fluctuation sum up to zero. Fluctuation sum up to zero, those forces. But drag will not sum up to zero because you have a purpose and there is a total force against it. So we will have a drag like this. Okay? It will be in the opposite direction of velocity and there will be some gamma. Let's call it microscopic friction. Okay? Do you have any questions at this point? Are you sure? Okay. Then we can write Langevin dynamics. Mass times acceleration. Mass times acceleration. Do you know what that means here?
Yes, time derivative.
Time derivative, right? Let me write time derivative. Is equal to minus gamma times v, which is drag, plus this random force, depending on time. This is Langevin dynamics. Let me just repeat that this part is drag or dissipation. This part is fluctuation. After a long series of equations, integrals, and whatnot, we will understand the connection between dissipation and fluctuation. Because notice that they are coming from the same origin. What is that origin?
Random motion of the surrounding particles.
Yes. It's interacting with lots of particles around it. So let's talk about some properties of this random force. What is the average of random force? If I average it out. 0, right? Very good. Then, what is this? What is it called? Correlation. So it's the correlation with a force right now and with a force after some time. Remember, we are calling this force random. So there should be no correlation, right? Except when it's at the same time. I mean, the force is when tau is 0, you are going to get r squared, right? When tau is not 0, what are you going to get? 0. No correlation. I mean, the kick that you receive here has nothing to do with the kick that you receive later on. A quick detour. You can change this and you will get some effects. Like, for example, hydrodynamic effects. Like the particle is moving and it's creating its flow, and you have to include hydrodynamic effects to understand swimming, etc., right? Or let's say what is kicking to this particle is not really mindless atoms, but some bacteria that would like to run and tumble. Do you know that motion of bacteria? They would swim, then would change the direction, swim that way, change the direction. So that directionality brings some memory effects. And that way, particle sometimes is being carried with bacteria to a point, and then they purposefully carry it to some else point. That is not happening, okay? It's just random. So, no memory, no hydrodynamic effect. No memory, no hydrodynamic effect. Good. What else do we know? Or we assume? We assume that probability of getting an R is a Gaussian. Do you have any objection to this one? So we are picking it out of a Gaussian. Now let's solve this. Let's solve this equation. So I'm going to start with the homogeneous part. So I'm going to ignore the time-dependent part. So I have just mv dot, let me put it with tilde, equals minus gamma v dot v. If you are not familiar with this, you can just ask questions, or you can even ignore this part. It's fine. Just a technique to solve this kind of differential equations. So we get rid of the time part, which was r of t. We will put it back very soon. Okay? Do you agree with this solution? This kind of solution? Yes? Now we put it back. We start with a particular solution. So we are going to try a solution in the form v of t is equal to v tilde that we have just found times some function of t. So we are going to propose a solution in this form, and we are going to find f of t. What is f of t? Hopefully. So let's plug it in. Do you remember our formula? Let me write it down one more time. mv dot equals minus gamma v plus rt. So let's plug this one in. What do you have? M times the derivative, time derivative of f, v0 e to the minus gamma t over m. The derivative of this one times this one. Okay, now it will be the derivative of the other one times the other one, right? You are following? Minus gamma f v0 e to the minus gamma t over m. Where did m go? This m go in this term. You know, it cancels out. You can follow that. Yes. The whole thing is equal to minus gamma times f v0 e to the minus gamma t over m plus r of t. Now, is there a cancellation here? Do you see? Are you happy? Yes. So you get a formula for f dot. f dot is r of t over mv0 times e to the gamma t. Let me give you some time. Gamma t over m. Do you have any questions at this point? No, the minus is gone. So the only terms that we have is this one and this one. And this term goes to the other side and it becomes minus. It becomes plus. Okay. So I can integrate this. I can try integrating it. Can you give me a moment? Mm-hmm. Is it hard? I'm missing a part here. Okay. Don't worry. Everything will be fine. So what is f of t? So 1 over mv0 times integral going from 0 to t r of t prime e to the gamma t prime over m dt prime. So far so good?
Yeah.
What is v of t? I have in my notes v of t written like this. Let's try understanding it together, okay? M integral 0 to t e to the minus gamma t minus t prime over m r of t prime dt prime. So how did I arrive at here? Well, I have v0 e to the minus gamma t over m times f as my solution, right? So the only point that I right now don't understand is why I have this term.
Because at t equals 0, the right-hand term is 0, but we want v at t equals 0 to be 0. So we the homogeneous term to specify initial conditions.
Ah, okay. So it's like whatever you said. Okay. But I don't. You must you must be understanding the right side of this. Do you?
Yes, of course. Yeah.
How about you?
No.
Yeah? No? Very good. Let me show you. Let me show you. What is f of t? So I'm going to do v0 e to the minus gamma t over m times 1 over m over v0, 0 to t, r t prime e to the gamma t prime over m dt prime, right? What I'm doing is I'm taking this one and I'm putting in. Okay? Once these are cancelled, I get 1 over m integral 0 to t r of t prime e to the minus gamma t minus t prime over m dt prime. How about now? Good? Very good, very good. So please interrupt me and let me explain these parts. This part, let me explain it later once I understand it. Okay? But besides that, what is the expectation value of Vt? the expectation value of Vt is V0 e to the minus gamma t over m. So I'm telling you that the expectation value of this is the expectation of value of this, and there's no term from here. Why I'm telling you that? Should I repeat?
Please.
I should really use this thing. So I'm taking the expectation value of this, right, which is the expectation of value this plus the expectation value of this, right? The expectation value of that includes the expectation value of this, which is 0. Okay? That's what's going on. So I have just this part. Okay, very, very good. How about it will be all good and fun. This lesson will be over and you will go home. You will eat something. It will work out, okay? Don't worry. So, concerning the expectation value of this one, we have the square of this one, 2 gamma t over m. But then we have a monstrosity, right? Because I'm multiplying this by itself and taking the expectation. By the way, how about the cross multiplications? Oops.
They
How?
have a single RT term, so 0.
So, exactly. So this times that will still get 1 RT. So its expectation value will be 0. That times that will get the same thing. This squared we already wrote. Now we are writing this squared. Okay, that one multiplied by itself. But notice that it's an integral times an integral. So it's a double integral. Yes, we will get a single integral eventually, yes. So I have 1 over m squared, integral 0 to t, integral 0 to t, rt1, rt2, expectation value, times e to the minus 2 gamma t over m, times e to the gamma t1 plus t2 over m, times dt1 times dt2. So far, so good?
Yeah.
These two things will give you something only when t1 is equal to t2. So it's Dirac delta t1 minus t2. Do you remember Dirac delta? Did I mention it in this course? No?
Passively. I think we mentioned it in quantum mechanics parts.
Okay. What it does is this. For example, if you have fx times Dirac delta x minus a, okay, going minus infinity to plus infinity dx, it just picks out the value at a. Okay? It's like a needle function at x equals to a. Only when the function hits that value, it picks up fxa. Okay? So that's going to happen here as well. It's only going to pick up the values when t1 is equal to t2. Let me write down what's the result of that. As I promised, we arrive at a single integral. Let me write it down from here. This is the term that we already wrote. Two gamma t over m e to the 2 gamma t prime over m dt prime. Okay, now you can take this integral. Why it is 2 gamma t prime over m? Do you see this? Why it is the same? Because
T1
T1
equals T2 equals T.
equals to T2, okay? And I've changed the name of T1 to T prime. So it's 2T prime, okay? Now you can take this integral and we have actually arrived at decent result. We know the expectation value of velocity goes like this. Plus r squared over 2 gamma m 1 minus e to the minus 2 gamma t over m. Okay? Do you have any questions at this point? What have we achieved? Let me show you what we have achieved. Especially when you take t to infinity, like v squared, t going to infinity, what do you have remaining?
R squared over 2 gamma.
Do you agree with that? Do you see that? Yes? Now let's point something out. What is this because of equipartition theorem? Equipartition tells you something about this one. KBT over KBT over M. Why? Because M times v squared over 2 equals kbt over 2. Do you remember equipartition? Now it comes back, the return of equipartition. So this thing is kbt over m. Right? The whole, this thing that we did was for telling you that r squared is 2 gamma kbt. That was the reason. Now, this connects fluctuation to dissipation. So you cannot have just any mv dot is equal to minus gamma v, but you basically have r of t here, but r of t is not just random function. It has a certain connection to the gamma. What is that connection? Let me just write it like this. It's square root 2 gamma kbt times a Gaussian. Hence, the dissipation is connected to fluctuation, because they have the same microscopic friction inside them. So you can't have, if you have a certain amount of drag, like for example, if you have a lot of drag in a system, you expect a lot of jiggling as well. If you have a lot of very little jiggling in the system, you expect very little drag. Yes? Very good. One final thing here. When you want to take this Langevin dynamics and put it in a computer, you have to be careful about one thing. You have to be careful about this random force. Remember that we say that, RT plus delta is r squared, right? Which is going to be 2 gamma kbt. However, this is because of like continuous functions, etc. If you are doing a numerical simulation, then you have RT and RT plus delta t. which you choose in your computer. Okay, so since you are going to actually choose a finite size delta t, this becomes, if delta t is, what I'm trying to say is, my point is, in the computer, we are going to take r squared as 2 gamma kbt over delta t. So we will include that delta t downstairs as well. Let me explain this more next time, but let's see the result of all this. So after all this derivation, we are allowed to write this thing inside our code. It's just Langevin dynamics. You start from, so what are we doing? We are actually simulating the big particle inside lots of small particles with this simple equation. What do we need? The magnitude, that is a Gaussian. You see 2 gamma kbt is here, divided by delta t, that I will explain more next time. But otherwise, it's just acceleration is gamma v plus rt divided by m, and then position is, next position is previous plus v times delta t times 1/2 at squared, yes? And v is updated as well with respect to acceleration. So when you run this, you can see that you can just compare the two things. Like, I have run this 100,000 times in 2 seconds. Obviously, of course, it will run really fast. It's just one equation. But it's a very good model of what was happening at the top. You know, the jiggling. Now you can take it to very, very long times, okay, with this. Next time, I will show you the connection of dissipation and fluctuation to diffusion, okay? And that will be your homework. Your homework will be to run this many times and show that it obeys the diffusion laws. Do you have any questions?
Fluctuation dissipation theorem also can be used to derive black body diffusion. Ama ölmüyor birazcık.
Do you see? I mean, every time you run, it goes to a different place. It's a random process. Okay, let's stop here.